The dynamic duo. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Cryptographic heart of TLS 1.3 by answering a crucial question. How do ECDHE and ECDSA work together? Many people learn about these two algorithms separately, but their true power is revealed when we see how they are combined in a real-world protocol. In this presentation, we will dissect their distinct roles and see how this dynamic duo provides both secrecy and authenticity for a modern, secure handshake. The two goals of a secure handshake. Before we look at the algorithms, we need to understand the two fundamental and separate goals of a secure handshake. The first is confidentiality, or secrecy. We need a way to establish a shared secret key so that we can encrypt our conversation and prevent anyone from eavesdropping. The second is authentication. We need a way to prove that the server we are talking to is the legitimate server and not an imposter or a man in the middle. A secure handshake must achieve both of these goals, and it uses a different tool for each one. Meet the players. A division of labor. To achieve these two goals, TLS 1.3 uses two different ECC-based algorithms, each with a highly specialized job. For secrecy, it uses ECDHE, which stands for elliptic curve Diffie-Hellman ephemeral. Its only job is to create a shared secret. Think of it as the key maker. For authentication, it uses ECDSA, the elliptic curve digital signature algorithm. Its only job is to prove identity. Think of it as the ID checker. They are not interchangeable. They are two specialists working together on the same team. The TLS 1.3 context. Ephemeral by default. It's important to remember the context of TLS 1.3. As we've discussed before, this protocol mandates perfect forward secrecy. This is achieved by using ephemeral keys for the key exchange. This means a new, temporary key pair is generated for every single session and then discarded. The E in ECDHE stands for ephemeral, which is why it is the perfect tool for this job. ECDHE is the mechanism used to perform this temporary key exchange. Two types of keys, two different jobs. This is a crucial concept to grasp. A TLS handshake involves two different types of keys. First, we have the ephemeral keys. These are temporary, used only for a single session to generate the shared secret, and then discarded. Their job is to provide secrecy. Second, we have the static keys, also called long-term keys. This is the key pair associated with the server's certificate, which lasts for months or years. Its job is to provide identity. The security of TLS 1.3 comes from keeping the jobs of these two key types completely separate. The handshake begins. Step 1. Client hello. Let's begin our step-by-step walkthrough of the handshake. The process starts when your browser, the client, decides to connect to a server. For the ECDHE part of the handshake, the very first thing the client does is generate a new, temporary, ephemeral ECC key pair. It then sends the public part of this key, called a key share, to the server in its first message, the client hello. The client is proactively starting the key exchange process. Server hello. The server receives the client's hello message and its ephemeral public key. Now it's the server's turn to prepare for the ECDHE key exchange. The server generates its own brand new, temporary ECC key pair just for this one session. At this point, the client and server have exchanged the public components needed to perform a Diffie-Hellman key exchange. But there's a problem. The client has no idea if the ephemeral key it just received is from the real server. The authentication problem. This is where our second goal, authentication, becomes critical. The client has just received a temporary public key from someone on the internet. How does it know it is talking to the real Google.com and not a man-in-the-middle attacker who just generated their own key? The ECDHE protocol by itself provides secrecy, but not identity. We need our ID checker, ECDSA, to step in and solve this problem. Step 4. The signature. This is where the two algorithms work together. To prove its identity, the server takes all the important details of the handshake so far, including both its own and the client's ephemeral public keys, and creates a digital signature over them. This signature is created using the server's long-term, static private key from its certificate, using the ECDSA algorithm. This signature acts as a cryptographic seal from the server, vouching for the authenticity of the temporary key it just created. Client verification. The server now sends its ephemeral public key, its certificate, and this new ECDSA signature back to the client. The client performs the crucial verification step. It takes the server's long-term public key from the certificate, which it trusts because of the PKI system, and uses it to verify the ECDSA signature. If the signature is valid, the client now has mathematical proof that the ephemeral key it received truly came from the legitimate server. The ID check is complete, and the man-in-the-middle attack is defeated. Step 6. The shared secret. Only after the client has authenticated the server's ephemeral key using ECDSA does it proceed to complete the ECDHE key exchange. Now that it trusts the server's key, it can safely combine its own private ephemeral key with the server's public ephemeral key to calculate the shared secret. The server does the parallel calculation. Both sides now arrive at the same shared secret, and the key exchange is securely complete. The keymaker has successfully done its job, thanks to the ID checker. Step 7. Key derivation with HKDF. The final step is to turn the shared secret, which is a point on an elliptic curve, into usable encryption keys. This is done using a key derivation function, or HKDF. The shared secret from ECDHE is fed into the HKDF, which then generates all the symmetric keys needed for the session. One to encrypt client-to-server traffic and another for server-to-client traffic. The handshake is now truly complete, and encrypted application data can begin to flow. Summary of roles. This table makes the division of labor crystal clear. ECDHE is used for the key exchange. It uses temporary, per-session keys to achieve its goal of secrecy and perfect forward secrecy. ECDSA is used for authentication. It uses the server's long-term, static key from its certificate to achieve its goal of proving identity. They are two different tools for two different jobs, and both are essential for a secure handshake. The full handshake visualized. This sequence diagram shows the entire flow we just discussed. The client sends its ephemeral public key. The server responds with its own ephemeral public key, its certificate for identity, and a signature to prove ownership of the ephemeral key. The client verifies the signature, and only then do both sides compute the shared secret and proceed to the encrypted session. This multi-step dance ensures both secrecy and authenticity. What if the certificate is RSA-based? This is an excellent question. What if the server's certificate contains an RSA key instead of an ECC key? The process is almost exactly the same. The key exchange is still ECDHE, because forward secrecy is mandatory. The only thing that changes is the algorithm used for the signature. Instead of using ECDSA, the server would use its long-term private RSA key to sign the handshake, using a modern scheme like RSA-PSS. The client would then use the public RSA key from the certificate to verify that signature. The roles are identical. Only the specific tool used by the ID checker has changed. A tale of two keys. This slide provides a final, clear summary of the two types of keys and their jobs. The ephemeral ECC keys, generated on the fly, are the domain of ECDHE. Their purpose is secrecy. They exist only for one session, and they provide forward secrecy. The static ECC or RSA keys, which live in the certificate, are the domain of ECDSA or RSA signatures. Their purpose is identity, they are long-lived, and they prevent man-in-the-middle attacks. Security comes from keeping these roles separate. The cryptographic symphony. It's helpful to think of the entire process as a symphony. ECDHE and ECDSA are two of the main instruments, but they work in concert with others. The certificate authority system provides the trusted root node for our signatures. A hash function like SHA-256 is used to prepare the data for signing. And finally, the HKDF key derivation function takes the result of the handshake and creates the keys for the main event. The bulk encryption performed by a symmetric cipher like AES-GCM. All these pieces must work together perfectly to create a secure connection. Conclusion. A perfect partnership. In conclusion, ECDHE and ECDSA are not competing algorithms. They are partners that perform two essential and separate functions in a TLS 1.3 handshake. ECDHE is the engine of secrecy, generating a fresh, untraceable key for every conversation to ensure forward secrecy. ECDSA is the guardian of identity, using the server's long-term, trusted key to authenticate the handshake and prevent impersonation. TLS 1.3's robust security comes from mandating this strict separation of concerns, ensuring that every connection is both confidential and authenticated. Final thoughts. Understanding this separation of roles is fundamental to understanding modern network security. Protocols no longer mix the keys for identity with the keys for secrecy, as this was a major source of vulnerabilities in the past. By using the right cryptographic tool for the right job, ECDHE for keymaking, ECDSA for ID checking, TLS 1.3 builds a much stronger and more resilient foundation for a secure internet. Thank you for your attendance. Please consider subscribing to the channel.